to give my talk, but I had memorized most of it, so it didn't matter. But anyway, that was my first presentation. We worked on models for dendritic spines. What's the function of dendritic spines? I'm not going to go through it, but here we are at a Gordon conference that Will and I both shared a presentation, and this was 1972. 1972. The other one was 73, I guess. The organizers were Walter Freeman, the guy who is now credited with first talking about gamma oscillations in the olfactory system. He studied the olfactory system. Jack Cowan was the co-chair. Jack Cowan was the guy who I talked about today, which developed the framework for mean field models with Hugh Wilson at University of Chicago. Here is myself, Will Rawl, Steve Grossberg. Nicholson, Charles Nicholson, was my roommate. He worked with another Freeman on interpretation of extracellular fields. This is Eric Young, a famous guy in the auditory field now at Johns Hopkins University. This is Alan Selverston, the guy from whose lab came all the people who worked on the stomatogastric ganglion of the lobster, some of the first central pattern generator stuff. This is Horace Barlow, the guy who talked about vision and reducing redundancy in sensory systems. This is Avis Cohen, who worked on the lamprey system back in those early days, developing mathematical models. Okay, so that's what that was. Okay, some of the people there. Okay. This was the 65th birthday symposium for Will Rawl in 1987. So let's see, what is now? Now is 25 years later. No, 25 and 65 is 90. He's going to be 90 years old, right? So this was, Will was an outdoors guy, so as one of our excursions, we just went out to the Potomac River and took a hike along the river. Steve Redmond, this is Dick Fitzhugh, this is Will Rawl, Gordon Shepard, John Miller, Bob Burke, Udan Segev, myself, Shihab Sharma, and this is Bill, forgot his last name for the moment, okay? Group of people that became famous in neuroscience. That was my good fortune. Here's the Dendrites gang, John Miller, myself, Gordon Shepard, Will, and Udan Segev, 10 years later. Okay, I think I will stop there. We've probably had enough. It's 8:20. Is it okay to stop there?
But we may continue till 10.
We can make.
I'm getting up at 4 a.m.
Okay, sorry.
We can stay here and have fun.
Next event, it's breakfast at 9. So we are quite limited.
Yeah.
But maybe some break, and if who wants
Okay,
can
yeah,
leave.
everyone on this time. A little
But
bit more.
if
I'll say a
someone
little
listeners
bit.
are still staying here, maybe.
I don't have much more to say. Okay? And the last few slides that I have are not
Body
as
language, I understand.
thorough as those in the preceding. I know more about the history that I told you than I know about the next. I'll tell you a little bit. So theory has been active in the field of neural oscillation. And some of the names of those people are Jack Byrne, Levitan, Dick Flint, Carmen Canavier, Rob Butera. One of the earliest papers on rhythms and phase resetting was by Raquel, Segundo, and Moore. I'll mention that. So these guys were among the first to see cellular bursting rhythms. Levitan and Levitan, but gosh, must have been before that. No, it must have been. I'm just showing this one because it's a nice example. But bursts were discovered before then because here was the first model produced by Richard Plant, 1978. Okay, this was a Hodgkin-Huxley-like model, and as I've been telling you, this kind of organization to the activity means that there's multiple time scales involved. Something slow to do the underlying slow wave, and then something fast to do the spikes. This is an example of what people call a parabolic burster. If you look at the interspike interval here, it's low here, it's high, and then it's low here. So that if you plot the period, or you plot the interspike interval as a function of position, it's going to look like an upside down U or a parabola. So this kind of burster is called a parabolic burster. And in many cases, you can block the spikes, say with a sodium channel blocker, and still see the underlying slow rhythm. So there's some slow oscillator that's driving the spikes. That's different than the kind of bursting I've been telling you about today, where there's some underlying bistability. In those cases, if you block the spikes, the bursts stop. Okay? This was one of the first papers on pacemaker neurons, 1964. Raquel Moore Segundo got involved in this, and one of the so this is looking at the they're driving a neuron with a periodic input, and what they're showing you here is the number of firing frequency, the firing frequency as a function of the input frequency. So on a diagonal like this, it means that the firing frequency is proportional to the input frequency. That means the number of spikes per cycle is constant. Okay, and it says here that over a range of frequencies, the number of spikes per cycle is constant. That's like a phase locking statement. And then if the input frequency gets too big, you drop down to say one spike for every two, or a smaller number of spikes for every 2 cycles. But the surprising thing was that if they put an inhibitory current in, they could get this kind of firing too. It's replotted over here. And it says that as you increase the input frequency of inhibition, you increase the number of the firing frequency. This is very surprising that if you get more inhibition, you get more spikes. It's a consequence of phase locking. It's just a consequence of phase locking. If you change the frequency of an oscillator, either plus signals or minus signals over a certain interval, you're going to keep phase locked. So you're going to have the same number of spikes per cycle. That's a good paper to read. Raquel and Maloney were among the first to show that you can get patterning between 2 neurons that are spiking with mutual inhibition. This was what I talked about in my lecture today, central pattern generators. So this is the first time that was put together, 1974. I think they had some adaptation variable here, Q. You see a slow accumulation, a slow recovery developing from the burst. But they were applying it to a system that looked just like the one I showed you today, the half-center oscillator. Mutual inhibition can lead to this alternating firing. They showed phase resetting and so on. a surprising thing was that in a system in which we knew that the interactions between neurons was inhibitory, that the experimentalists were observing synchronous oscillations. This came out of the work of people studying the thalamus. They were actually interested in sleep rhythms. And they knew that sleep rhythms were generated in the thalamus between an excitatory population and an inhibitory population. The excitatory cells did not talk to each other. The inhibitory cells did talk to each other. In vivo, Stereotti, the guy who did a lot of work on these rhythms, claims that he had cut the connections between the inhibitory neurons and the excitatory neurons, and there was still a synchronous oscillation in the inhibitory population. A guy who was a postdoc with me at the time, Xiaojing Wang, who's now famous in his own right for working on decision making at Yale University, was with me at the time, and we were starting to get into this rhythmic system, the thalamic rhythms. And we just really were so guided by the half-center oscillator, where mutually inhibitory cells wanted to go like this, anti-phase with each other, we couldn't imagine how you could get inhibitory cells to go together. So we had to come up with a scheme for doing that. Our scheme was, if the inhibition is slow, you can imagine that cells could go up together, turn on an inhibition that pushes them both down, and that keeps the cells down for a while if it takes a while for the inhibition to die away. So if the time scale of the inhibition is slow enough, the cells could slowly rise again and then re-excite each other, or re-excite on their own, and create another cycle like this. So we made this simple half-center oscillator with Morris-Lepar models with a very slow negative feedback, and, whoops, whoa, oh, where is the picture of the slow wave? Here, slow synapses. We made the synapses have a slow recovery time, and so we could get these mutually inhibitory cells to synchronize together. Well, this became a thing that other people have then looked for at the spiking level. These are slow waves, thinking about what's going on in the bursts in the thalamus. But with spiking neurons, people also could find similar things. If the inhibition had slow time scales, you could get cells to synchronize through mutual inhibition. This became part of the story for understanding a mechanism for gamma rhythms, having mutually inhibitory cells synchronize. Okay. I'm not going to bother to go through this story about waves. I'll do it only because I want to show you a movie. Okay? If the movie comes up, fine. If it doesn't, we're done. Okay? So they knew that rhythms were generated in the thalamus. And these are the kind of rhythms that occur in sleep, like in drowsy sleep, not deep sleep, but also in deep sleep, another frequency. Spindle rhythms occur in drowsiness. They're also similar to the rhythms that occur in absence epilepsy, in petit mal epilepsy or absence seizures. These are the kind of rhythms that occur. So David McCormick, a very skilled in vitro electrophysiologist, made a slice of the visual thalamus. So up here are the inhibitory cells, Down here are the excitatory cells in the thalamus. He put an array of electrodes in this system, and he was seeing waves propagate along this bank of electrodes, this array of electrodes. And each one of these events recorded with these extracellular rays was a spindle event. Okay? In this case, the thalamic reticular nuclei cells the inhibitory cells are making a burst on every cycle. The excitatory cells are bursting on only every other cycle. He did some very beautiful experiments here where he would block one kind of inhibitory synapse, the fast one, or block the slow one. If you block the slow one, you didn't change this rhythm. It was as if the slow synapses didn't participate at all. Then he blocked the fast ones, and this rhythm changed. Now the thalamic cells fired on every cycle. They burst on every cycle. Okay? So we made a model, a distributed model of the inhibitory cells that can talk to each other, the excitatory cells that do not talk to each other, but only communicate through the distributed nature of the inhibitory cells. Okay? We published our paper in the same journal of neurophysiology that Alonza Stex and McCormick and Sejnowski published a very similar thing. We arrived at these simultaneously and independently. So I have an animation here. We'll see if it works. Okay. What you're going to see now is the inhibitory cells going up and down. That's an event, a firing event, and the excitatory cells going up and down. I think the movie starts with activating some inhibitory cells. So you'll see these guys go up and these guys go down because they're getting inhibition. And then they will rebound. They will rebound from that inhibition, create a spike event that sends excitation up and moves the wave along. This is a curious kind of traveling wave. Let's see if it works. Yeah, looks like it's not working. Okay, somehow my file is not in here properly, so I can't show you this this video. I'm sorry. I'll have to bring it into my PowerPoint. Remote control. Yeah. It's okay. We'll just have to we'll have to skip over this. Maybe there's another one. Maybe the next one will, but I doubt it. No, it's not going to work. Anyway, the curious thing, no, I can't try to explain it without visualizing. It doesn't make sense. I think, I can tell you this, for those of you that didn't see this. This kind of a model with mutual inhibition between two cells or populations of cells is the same kind of model that we are using now. Okay? It's in a completely different context. It's in the context of perceptual bistability. This is an example of perceptual bistability. This is an ambiguous scene. Okay? You can perceive the two faces, or you can also perceive the white vase in between. If you stare at this image, your perception will alternate every few seconds between the vase or the faces. But the image on your eye is constant. So there's something going on in your cortex which corresponds to one population being dominant or another population being dominant. So we use these same kind of models that I showed you were first invented in the 1970s for driving antagonistic muscle groups. Okay? This is for two neuronal populations competing for dominance. This percept or this percept. Okay? And so we are working on these kind of models for visual ambiguous scenes as well as auditory ambiguous stimuli now, and trying to get sense out of what might be going on through neural populations that we don't even know where they are. Okay? People have seen with MRI imaging, with even electrical recording in monkeys, perceiving ambiguous scenes or binocular rivalry, neurons coming on, going off, coming on, correlated with the kind of rhythms that you see in percepts. How would you do this with a monkey? How would you confirm that the monkey's neurons are going together with the monkey's percept? Okay? Logothetis has trained his monkeys to report their percept. Okay? So in that system, we can have electrophysiology in visual cortex that shows oscillations or alternating activity, or at least some neurons coming on and going off in synchronization with the person. Okay, I think I'm going to stop here. I'm sorry you didn't get to see this movie. It's really kind of fun.